is any well-defined or related, well-defined or related list. Okay, list or collection. List or collection of objects. These objects can be human or can be, things if you like. So that's going to be the definition of a set. Of course, if you're going to be pure mathematician, it's going to be quite different. Lots of argue about it, but this is not going to be our case here. We just accept it right away. Okay, that's going to be the sets. We have a notation for the sets. The set's going to be denoted by the, okay, that's it. So sets in this course are going to be related, denoted by notation, are going to be denoted by the capital letters like A, B, okay, X, Y, etc. So these are going to be the sets. The object inside are going to call it the members, okay? So the objects inside the set of the set, objects of the set are called members, are called its members. Okay, it's going to be its members or elements. Two expressions that we're going to use. Members or elements of the sets. Okay, elements of the sets, and usually denoted by R, going to be denoted lowercase numbers or letters by, this is it, something like A, B, X, Y, etc. This is not a standard one. You may try something else yourself in some occasion, but these are the standard one that we usually use. Okay, any question? Now there are some special ones. We get to more general of the sets in chapter 6, but now we have to build up some notation and definition that we need for future. So some special one that we are going to use without any definition. Okay, special sets. For the special one, the first one. Okay, the first one is going to be counting numbers or natural numbers, which is very important in this course. Okay, counting the numbers that we use to count. Counting numbers or natural numbers. Okay, or natural numbers set. Most of the time, this is going to be our main definition, if you like. So this set would be denoted by n for the natural, and these are going to be the collection of the numbers, which is going to be 1, 2, 3, 4, etc. So that's why we call it discrete domain, because it's a dot, dot, dot. Okay, 1, 2, 3, 4, 5, 6 is going to be considered the natural numbers. Sometimes some people may add the 0, but in this course, no, we don't add the 0 to the natural numbers. Okay, that's the first set. Any question? The second set that we are going to have, okay, what is going to be the second one? The second one that we use in this course is going to be integers. Okay, integers. Okay, for the case of integers, you know that integers is going to be, you get the 1, 2, 3, 4, 5, 6, you put them on the number line. Then if you put the mirror image of these numbers, which is going to be -1, -2, -3, -4, and the 0, which is at the center. So all of them together is going to be integers, okay? So we denote it by Z in this course, Z, and this is Z. You get the 0 at the center, then you have a 1, 2, 3, etc. Then the mirror image, which is going to be a -1 and -2, then etc. So it's an infinite set. So it's cover the, the positive natural numbers, which is going to be the positive integers, and the -1 and the 0. Okay, so if you see the Z in this course, this is what we made, Z. The positive integer in this course is used from time to time, so we are going to give you that definition too, especially in your book. The positive integers, there are a couple of cases that we're going to use. So if you see this notation, if you see the Z with the positive sign on the top, so this is less like the, like the natural numbers. So this is going to be simply 1, 2, 3. Okay, 1, 2, 3, 4, etc. Which is the same as the set of the natural numbers. Okay, in mathematics, of course, they use a little bit of different notation. You see this is the notation that we use for the natural number. If you say this one is the same thing. No, I'm not going to use it in this course. And for the Z, we're just using, the double line here. But we use the N, Z, and the Z positive. Okay, yes, question?
Would Z negative be all negative numbers, or is just the positive integers that has this Z plus?
In this course, the positive integers are the one that we are interested in.
Got it. Thank you so much.
Because our domain is going to be positive numbers in the computer science. But we can define Z negative too. But I'll just give you this one because it's the one that we're going to use. So when we see it, so we know what we are talking about.
Perfect.
Okay, remember without 0. 0 is not going to be in this set. There is a special function in computer science that the range of those functions are going to be these numbers. That's why we need it. Okay, so this is going to be one. Any question? The next one, of course, is we are going to have one chapter on this one later on. And this is the rational numbers. Or some people, they say fraction. Okay, rational numbers. This would play very important roles in our construction of those systems that I talk about it. The rational numbers is a ratio of two numbers, ratio of two integers. Any ratio of two integer, of course, the bottom one cannot be 0, you know that. It's going to be called a rational number or a fraction. So basically a rational number would be denoted by Q. Okay, Q, and this is going to be different. We cannot list all of them, so we give you a definition type. So this is going to be a number which is going to be of the form of the A over B. Okay, A over B. This A and the B, so A and B are going to be, integers. Okay, they are going to be integers, but with one condition. With the condition that B is, condition that the B is not 0. So always, any time, if you tell us, A over B, suppose A over B is a rational number. So the rational numbers, that this B is not 0. Okay, it's like 2/3, 1/2. Okay, 5, 7. Okay, -15. And they are going to be all rational numbers. Okay, a number that can be defined as can be identified by the ratio of two integers. We get back to this one. It's very important one. You said number of the question related to this, this set in future. Okay, any question? Of course, there is going to be irrational number. We are not going to be interested for the time being. We get back to it. So we're not going to consider it for the time being. And of course, the real number system. Okay, the real numbers. From time to time, we're going to use this one. In your case, you work with these, the integers and the natural numbers in your set, because it's a discrete dot, dot, dot. But when you get to the number, real number, it's a kind of, it's going to be all the numbers between two given numbers. So it's not going to be popular for case, but this is it denoted by R if we need it. So we denote it by R. And you know that this is going to be what? This is going to be an interval that starts from -infinity. And this is going to be a positive infinity. And if you like, the 0 is here and the 0. So any number on this number line is going to be called a real number for the time being. Okay, it's not going to be good for us because we like this discrete structure, this discrete dot, dot, dot. Okay, it's like, it's like you have two type of watches, if you like. Some of them are going to be digital. The other are not going to be digital. The digital one is like the discrete one. You look at your watch, now it's 12.5. Then later on, you have to wait to see 12.6 if you like. But if it's going to be the usual one, a clock, if you like, you will see it. So it's a kind of comparing. So we are not going to use this one, and we are not going to use the next one, but we write it down to get the complete sets of numbers. It's complex numbers. Okay, complex numbers, you know that we know that by C, and we are not going to see it, the number of the form of the A plus BI. But basically, that natural numbers, positive integers or the rational numbers are going to become that is going to be repeated over and over. Okay, so we are going to consider this group to be a special for our case. Okay, any question? So a set is just a collection of objects. Most of the time, it's going to be a collection of numbers. If it's going to be some famous number, these are going to be one that you have to know it. As soon as we get to this type of, you see the notation, you know what we are talking about. Okay, any question? Now we need a little bit more rules to go on. We have a couple of more notations that makes things easier for us to express those logical expressions that we are going to have in future. Okay, so these are going to be a standard notation that I'm going to use, and you can use it. Notation or notations. Now, the first famous notation is if a member of a set, if you want to identify that something is in your set, this is the notation that we're going to use. So if X is an element, is going to be an element, a member, element of the set A. So this means if A is in A, if X is in A, then we usually write, okay, this is the notation. We write, this is it, X belongs to, you see this notation? X belongs to A. X is in A. Okay, belongs to, so this notation over here, you see this one? This notation means belongs to. Okay, belongs to. Okay, so belongs to. And that make it easy for us to express our idea. So if the set A is given to you, and the members are 1, 2, 3, and 4, if this is going to be the case, then you can see that the 2 is in A. So if you want to say that the 2 is in A, you write 2 belongs to A, belongs to A. So you have it in your assignment, your first assignment. They ask you which of those conditions are going to be true or false. So if they give you this one, you know that this means 2 is in A. So you know that it's going to be true. Okay, and 2 is in A, and for example, 4 is in A, 4 belongs to A. Okay, but as you can see, there is no 5 here. So, but if you have 5, you can say that the 5 is not. This is the way we write it down, okay? Is not in A. Okay, so belongs to, and this does not belong to A. Look at this notation. Things make things easy for us, and we're going to use it quite a lot. So get to know it, belongs to. Okay, any question? Now that we have these sets, you know that any system that you introduce, okay, any system you introduce, you have to tell us how we're going to compare. You see, when we talk about the numbers, you have to tell us how we're going to compare the numbers, what type of notation are going to use. Okay, so in this case, it's going to be, we want to know how to compare two sets together. So we have to tell us when you are going to consider the set to be the same. Two sets are going to be the same if they are, or they are equal to each other if they have the same members, the same numbers. Okay, so this is going to be the next notation. The next notation is going to be if, okay, if the sets, if the sets A and B, okay, the sets A and B have, if they have the same, they have the same member, exactly the same one, same members, then this is it, we write, then we write A is equal to B. Okay, they must have the same. When we write the members of the set, if you have a repetition, you see, there's going to be no repetition and no order. So if you repeat the members or to change the order, nothing would be changed. They are going to be the same thing. Okay, so let me just finish this one. So if you want to write this one in symbolic form, this is it. So you can say that A is equal to B. A is equal to B. Let's say if and only if. You see, if and only if for any member. If you have a member X is in A, okay, then that would implies that X is also in B. So this means any member of A is also a member of B, and okay, and the other way around. For any member X is in B, that would imply that the X is also in A. So if you want to prove it, if you want to use its symbolic form, that's going to be the case. But basically, this means they are going to be the same. Okay. And so, for example, if you look at these two sets, for example, if you have these sets, if A is equal to, if A is equal to the 1, 2, and 3, okay, and then we have the B, and B is equal to 1, 2, 3, and 2. See? 2 is repeated. When you write it down the sets, you repeat that one, of course. Maybe that would be related to the something. But when you want to compare them together, you see the member of the sets are 1, 2, 3. And this is the same for this one. So the repetition or the order is not going to be important. So these two sets considered to be equal to each other. Okay, if it's going to be the case, then as you can see, A is equal to B. A equal to B because the members are the same. But you know, you get this repetition. Okay, any question? So two sets are the same if the members are the same. When we write the sets, no order, okay, and no order, no repetition. In mathematics, we have different things, you know, not in this course, of course. We have another expression, we call it family. We have the family, we have the sets, then on those, it would be important to, if you get this repetition, but not in these sets, not in this course, no repetition. Okay, any question? So now we have the comparison to how we're going to do. Now there are some other things that we have to do to be able to take care of this system. You may have a set with no members, okay? So we have a notation for that one, and it's going to be very important for us. So if a set A, if a set A has no element, no member, has no element or members, then we call this one an empty set. Okay, then A is called, okay, A is going to be called an empty set, empty set. Set with no elements. It's going to be empty sets. The notation that we're going to use, okay, in this case, so it's going to be in, okay, in this case, the notation that we're going to use, we write, okay, this is the notation. You may write this notation, you see, that is going to be the case, or the empty set, or, okay, or you may write this one, a just empty set, nothing else. You are going to use this a couple of times through this course, even if we get to the final. So make sure you use the correct, okay, use the correct notation for the empty sets. I should remind you something that the people they write and they missed a point on the test, and that's the one. You see, don't do this one. Note that. Okay, note that. This, you see, sometimes the people write this one. Look at this one. This is not an empty set because there is something in it. This is it. Okay, so this is a not. Make sure don't do it. It's not an empty set. Not an empty set. So make sure don't make this mistake for the empty set. So two notation, you can use this notation, okay? You can use this notation or the other one. There is nothing in it. Okay, any question? So that's the empty set. Now, when we talk about it, for example, when we talk about the domain of the algebra of the variables, we consider the domain to be all real numbers. So we say x is a real variable. So this means x can stand for any real number. So we have to have a kind of a reference or the big source for these sets, where these sets are coming from. Okay, we need something for it. So we are going to introduce, we assume that all these sets, all the possible sets, if you put them together, we have a big one, if you like. We have the source. That source is going to be called universal sets. This is very controversial in mathematics, the way we are going to create the universal set, and it's quite interesting if you are going to be interested in logic of the, okay, mathematical logic. But again, as I told you, I can explain it if you ask me, but we just take them as is, okay? Don't be so sensitive, if you like, about that part. It's just the introductory level. So what is that? We assume that the members, so they say, oh, where these are coming from? Okay, is there a source? Yes, there is a source. So that's a source, the members. Okay, the members of all possible sets, all possible sets, and their study or and their investigation, if you like. All of them. They belong to, okay, they belong to some fixed, if you like, some fixed source, largest possible set, largest set is going to be called largest set called the universal set. You must know this expression through this course. Okay, the universal set. So we assume all of them are going to be a member of a big one. That big one is called a universal set. The universal set is going to be denoted by U. It is denoted by U. So if you use this expression, the universal one, you know that, you know, it's very controversial that how do you know that this universal set doesn't exist? And we have different schools, if you like, or different ideas or beliefs in mathematics, you know, that some people believe this one. You know, George Cantor is the one who created all these ideas to start with, English mathematicians. And later on, we have some other people like Bertrand Russell, okay, René Descartes. And so there's going to be quite a lot to talk about it. How do you expect it? How we're going to create it? But we accepted that, yes, there is a set, okay? So we're not going to get into those type of ideas. Okay, any question? So there is an empty set. We need this expression. Without these two, the smallest one, if you like, and the largest one, we can't go on with our system. So there is a set with no elements. We call it empty sets, and we assume that all the sets are coming from a source. That source is going to be called universal sets. It's a sets of sets, if you like. Okay. Any question? Now a couple of more to be able to do something about these ideas. Okay, now the next one is we may be interested to just compare these small sets that we're going to have. So you may have a big set, a collection of elements. If you just pick a sub collection, just pick some of them, some of the members, you are going to create a new set, but your set is a kind of a smaller than the bigger one. So this smaller one is going to be called a subset. So what is going to be the subsets? Again, we get to this one, subsets. That's SUB. Okay, subsets. So if A and B are going to be two sets, if A and B are given sets, then B is going to be called a subset. Then B is going to be a subset of A. If all the members of B are in A, B is a subset of A if, okay, if every element in B is going to be is also an element of A. Element of A subset of A. Okay, a subset means sub-collection. That's going to be the one. The notation that we're going to use is this one. Okay, so the notation is we write, that's a notation, we write B is a subset of A. B is a subset of A. We write this equality because B can be equal to A. So A is a subset of itself, if you like. Okay, so if you like symbolic logic, symbolically writing down this format, so we say that B is a subset of A. B is a subset of A if and only if. We're going to make it better in future. If and only if for every, okay, for every X is in B, okay, that would implies that X is also in A. Okay, so B is a subset of A. B is inside A, if you like. That's going to be the one. We are going to get back to this one in chapter 6, and we list all the subsets of the given sets. We have something, we call it power sets, but we don't want to talk about it now. So just a notation in this part, and very easy example. We have another expression is that you see B can be also equal to the A. If you would like to have a strict one, if you want to have the B to be strictly less than A, this means B not equal to A. In that case, B is going to be called a proper subset. And we are not going to use it, but since you have a couple of problems in your book, so we want to make sure that you know how to do it. So note that if B is not equal to A, not whole of A, and B is a subset of A, this means it's strictly less than A, if you like. then B is going to be called a proper subset. B is going to be a proper. Okay, it's going to be a proper subset. Proper subset of A. And we usually write, and we write B a subset of A. In some books, they don't care. They give you this one for both of them. But for the sake of, there's just a couple of problems that you have in your book, you have to consider it, okay? We are not going to work with the proper subset when we get to the chapter 6 and the application, but just nice to know it. Okay, a proper subset of A means that it's a sub-collection. It's not all the sets A, okay, because A can be a subset of A itself. Okay, just one example to finish it, but we get back to this one quite a lot in chapter 6. And chapter 6 is all about the sets. Again, when we get to the 6, the part that we need, we just collect them all together in very big one section and we finish it. And so we need them to be able to get to the definition of a function, okay? So the example is just, we are not going to ask you to list, but we give just 2 to compare. So suppose the set A is given to you, and this is going to be 1, 3, okay, 1, 3, 4, 5, 8, and 9. That's one set. Okay, and we have B is equal to the 1, 2, 3, 5, and 7. Okay, and we give you another set. We give you C equal to the 1, 5. Okay, these 3 sets are given to you. Can you tell us which set is the subset of the others?
So C is going to be a subset of B and A.
That's it. C is a subset of B and A. Yeah. And is the B a subset of A?
No, because A doesn't have 7.
Very good. Excellent. Yes, this is it. So this is going to be the case. So then, as you can see, yes, C is a subset of A because we have 1, 5. 1, 5 is here. Okay, so C is a subset of A, and it's a proper because it's a smaller. Okay, and yes, C is a subset of B because 1 and 5 is here. So it can be subset of B. It's all you have to do, or you can say. But as we talk about it, B is not a subset of A. It's not because B got the 7. Yes, we got the 7 here, but there is no 7 in A. Okay, so for future, look at this one. The empty set, remember the empty set? The empty set is a subset of any set you like. Because there is no element in the empty set, so we can say that any elements in empty sets belongs to A. Because you cannot prove anything otherwise for us. Okay, this could be one. And of course, the other one is A is a subset of A. Again, there are quite a lot. We are not going to get to it for the time being.
Because I have a very quick question.
Yes, yes.
Imagine if we have another set named D, and in it we have 1, 1, 2, 2. Would it be the subset of B or not? Because we're repeating the numbers, right? And
the repetition is not important.
It's not important. Okay.
No, just the elements. So it's going to be 2, 2, 2, 2, 2. You consider as a 2 only. Okay. So we just check to see if the elements of the D is going to be in B. So it is in B. Okay. Not for the repetition. Okay, then your main job is when we get chapter 6 really is one of these sets would you see 1 out of 5. For example, we would like you to list all the possible subsets. The way we do it, we can have a subset with 1 element only, a set with 1 only, set with 5 only, then set 1 and 5. In this case, it's going to be quite a lot. So if you list all the subsets of the given sets, that set is going to be called power sets. That's the one that you use in Cartesian for two nice functions. But since we don't have the function and the tools now, so we cannot talk about it. And we get back to it. We get back to it in chapter 6, but we need it for the time being to be able to get to. Okay, so wait for the good one. Okay, any question? So remember, our idea is we try to give you a kind of a preliminary definition of a function. So this is the way, you know, we're just getting small bits of the sets to be able to take to get to that one. And that's why the next operation of the sets is very important. This is going to be we call it the product of the sets. Okay, how are we going to define the product of the sets or Cartesian product of the set? This is the one that we are interested in to get the notion of the function and the relation. And when we get to the final exam, we come back to it. We get the chapter 8, very full chapter. Let's start with the Cartesian product again, but we need it. And we are going to test you on this one, okay? So basically, this is the part that we are going to be interested in and important. Okay, what's going to be Cartesian? Okay, Cartesian products. Probably have read about this type of products in calculus. Okay, Cartesian product. So make sure you know this part from this section. That's the main one that we needed, and we come back to it twice during the course. Okay, what's the Cartesian product? So if two sets are given to you, so if I write it down and then I explain it again, if the sets A and B are given, okay, are given, then the Cartesian product. Okay, that's it, Cartesian product. Some people, they say a cross product, which is not the same thing really, but I write it down because it's in your book. Or cross product, use a cross product for the vectors. Okay, just call it Cartesian product. Okay, the Cartesian product of A and B, is going to be denoted, okay, it's denoted by this notation, denoted by A cross B, or A times B. That's one. And it's going to be defined by a set of an order pair, and is defined by, that's a definition. Definition is going to be A cross B is equal to a collection of all, okay, collection of all order pairs A comma B when A belongs to A. The first component is in the first sets, and the second component is in the second sets. Okay, it's a kind of a set of a collection of order pairs, if you like. The first member must be in the first set, the second is going to be in the second sets. Okay, the order is going to be very important. These elements, okay, the elements A comma B, you know that it's going to be called order pair in A cross B, if you like, are going to be called, okay, are called order pairs. Order pairs. Okay, order pairs of these sets of A and B. You know that in the rectangular coordinate system in R2, you have the order pairs of numbers. In calculus, you identify a point, okay, with coordinate of 1, 1, 2, x-axis and the y-axis. It's going to be a same thing. Okay, so it's A and the B can be numbers, or A and B can be object. Okay, these are going to be order page. And in order to find out how many members are going to have, depends how many times use the A and the B. There is a rule that we call it product rule. We use it at the end of the course later on. But just for the time being, give you the hint, because you are going to list all these members. We don't want you to miss anything. You see, if the first set would have 2 elements, and the second set would have 3 elements, then A cross B would have 2 times 3, which is 6 elements. We call it the product rule in future, but for the time being, I give you the hint and you can use it. So if A has M elements, and B has N elements, Okay, M and N, then A cross B has M times N elements, the product. It would be very important for us when we get to counting method in future at the end of the course. But it's okay. It's very good to know it for the time being. Okay, so that will help us when we want to list it. We are not going to miss any of these. Your job is, we give you one question on this one on the first quiz. So your job is, we give you 2 sets and we ask you to give us the product of the sets. Okay, so let's find out. Any question? You know that Cartesian product is coming there from the name René Descartes, the one who created, French mathematician and philosopher, created the XY coordinate for us. So that's why we call it Cartesian products. Okay, any question? So get your first example and your first job. And we're going to do quite a lot of these type of problems towards the end of the course. But as now, we can have the following. Okay, so 2 sets given, and then they ask for the Cartesian product. So suppose we have A equal to the 2, 3, and 4. That's the first set. And then we have a B equal to, the second set is going to be 4, 5. That's a set. I would like you to find the following for us. Okay, find the following. Find the following sets. That's your job. The first part, they ask for the A cross B. Okay, the second part, they ask for B cross A. And the third part, they ask for the B cross B. Okay, would like you to list all the members in this case. Okay, are you ready? So we do the first one. Solution. Okay, for the first part, that's it. I just remind myself that you see A got the 3 elements, 1, 2, 3, and the B 2. So 2 times 3 would be 6. So I remind myself that the A cross B has 3 times 2, which is going to be equal to the 6 elements. So this means you are not going to miss anything. And the members are given to, you must be given as an order base. Okay, so it's going to be A cross B equal to the order base. So you're going to pick one element from A and you match it with all the members in the B. When you are done, we come back. Okay, so we start with a 2, so we can have 2, 4, and we get 2, 5. So it's going to be 2, 4, Then the next one is going to be 2, 5. Remember, you must use parentheses for these, bracket type for the sets. In some books or some part, they use even bracket for this one, but not in this course. Remember, the order page is parentheses 2, 4, 2, 5. Any question? You're done with the 2. Go to the 3 and match it for the other one. So 3 can be matched with 4, or again 3 and 5. So we are done with the 3. Then we go to the 4 and we repeat it. So you can have 4, 4, or you can have 4, 5. That's it. You count the 1, 2, 3, 4, 5, 6. So this is going to be the order page and the product. Any question? Okay, so it's very important. The order is important. So the first member must belongs to A. Okay, the first member must belongs to A to get these numbers. Okay, so this is the first one. Ready for the second one? The second one is B cross A. You just switch the members. Okay, you switch the member because you want to start with A. Okay, so your first member must be from the A. Okay, so this is going to be the one. So this is going to be the case. Okay, I just switched them. You see, this is like 4, you have it already here. So it's going to be 4, 2, 5, 2, 4, 3, 5, 3, 4, 4, and the 5, 4. So that will be B cross A. So they are going to be 2 different things. It's not ordinary multiplication that you say they are equal to each other. You know that. In ordinary multiplication, 2 times 5 would be 10. And 5 times 2 would be 10. But it's not, it's different. It's something different. So make sure that you know the difference. Okay, question? For the last part, we just want to know that we can have, we can multiply a set by itself. It doesn't matter. You see B cross B. B got 2 elements. So it's going to be 2 times 2, which is 4 elements. So just remind yourself for the part 3. Okay, remind ourselves that the B cross B. Okay, B cross B has, has 4 elements. 2 times 2, 4 elements. Okay, so you know that you have to these 4 elements. It's going to be B cross B. Again, you pick the one element, which is 4, and you match it with the 4 and the 5 again. So 4 can be matched with the 4, or can be matched with the 5. Okay, then we get the second element, which is 5. So we can have the 5, 5, or we can have 5, 4, or 5, 4, and 5, 5. It doesn't matter. Okay, so 5, 5, and 5, 4. So you have 1, 2, 3, 4 elements, which is going to be the case. Okay, so these are going to be one. This is for 2 sets. We can consider getting, we can multiply even 3 sets together. But these are going to be done. We are going to use in future. Okay, any question? Can you give us some examples of these order pairs in everyday life? You see, there is a reason that you put the 2 and the 5 together, 2 and the 4 together. Okay. Any example of the order pairs in everyday life? I can give you one. You see, the first one, suppose the set A is your names, and the set B is going to be your birthday. So I can match you with your birthday. You see, with your birthday, that.
But there's a very small problem here. One person cannot have 2 birthdays, right?
It doesn't matter.
But like if I'm 2, I cannot have 4 and 5.
What's your question again?
I'm saying like it would be a good example, but for this specific example, it wouldn't work because We have
It
two
does
and
work. Why not? Why not?
because we have 2 and 4 and 2 and 5. So
Doesn't matter.
if I'm 2, I cannot have 4 and 5 as my birthday, right?
No, you can't.
Exactly.
No, what do you mean?
I mean, if I'm object 2 and if 4 and 5 are birthdays,
No, no, not
I
just 4 and 5. You see, A is a list of all the members in this class,
yeah.
and the B are their birthday. So I cannot just put them together. It
Because
doesn't
we
matter.
only have two birthdays.
You may have all the people in this class would have the same birthday.
Oh, that's true.
It doesn't matter.
That's
It
odd and
is
true.
no. You think about something else. No, no condition. You just say order base. You
True.
see, we just want to collect them together. Any example in everyday life, order base. Just think about it in everyday life when you go shopping.
A could be cars, and then B could be their license plate.
Of course, yes, very good. Yes, cars and license plates. We can put them, we can match them together. Very good. Any more examples in everyday life? I just want to know how important they are really. Any more? Where do you go in everyday life?
Could be a state and then a city.
Yes, a state and a city. Anything else? Anything else in everyday life? There are some very popular ones that you miss.
Could be clothes, like shirts and pants matching for an outfit.
Okay. Anything else? Where do you get your coffee in everyday life? You get from your Starbucks. You see, as soon as you arrive at the Starbucks, you just look at the menu. The menu is just a product of two sets, order based. The first part is the name of the produce or the product or whatever it is, the coffee, the brand. And the second part is the money that you have to pay for it. You see, they give you cappuccino, what, $4, white mocha, that. So
I
they
have a
match them
very quick
together.
question. I have a
Yes,
very quick question. So I'm still not persuaded that the birthday example is going to work here because if if A is the list of the people in the class, so
yes.
imagine 2 is Sam, 3 is Brian, and 4 is I don't know, like Samson. So if I'm Sam, I cannot have like if 4 and 5 are the birthdays, I cannot be born at 4 and also 5.
No, you can't.
So basically, A cross B is cannot be a right set, right? Like the members of A cross B cannot be.
No. You see, I'm talking about the order base. What you think about it, you think about something else. You think about the function. It's not a function. It's
Oh,
just,
okay.
that's it. It's just a listing. It's just a listing of the name and the birthday. So what's wrong with this one?
Oh, so you're not talking about A cross B. So you're just talking about A and B.
That's it. Yes, A
Oh,
and B.
okay. I
Just a
was in the
collection of
wrong.
objects.
I was
Collection
in
of
the wrong.
objects. No,
Got it.
no,
Thank
it's
you.
collection of objects. Then later on, we may put something, more restriction on it, but not now. It's just a collection of relations, not relation even. It's just an
Okay, now
order
I got it.
base.
Now I
You see a
totally.
Starbucks, go to the what? Go to Burger King. When you arrive at the Burger King, it's just you see the order page. You go to Albertson. As soon as you arrive, you will see the list of today's produce. Okay, the names, you see the names and the that. Okay, so it's just a collection of these order pages that we call it. Okay, we put them together.
Yeah, I totally got it. Now I know what my
Yeah,
mistake
yeah,
was. Thank
you
you.
go to the gas station. You see, the first one is going to be number of the miles. The other one is going to be the money that that you pay for it. So when we have different types, we just list them together. Okay, so it's a collection of, a collection of order pairs. So these order pairs are going to be, decided later on. So the first one is you, Facebook. The first one, the set is you only. The other part's going to be your friends. So you match yourself with your friends. So you have a collection of order pairs. Okay, that's going to be the one. Now, the definition of a relation and the function is going to be the next step. That I leave it for next time. We are just right on the part that we are interested in. These are all preliminaries. So what we're going to do is we define a relation. You see, in order to have a relationship, you need a pair. To have a relationship, you need a pair. You see, 4 and 5 are related to each other. So if two sets are given to you, like the one that we did, if two sets is given to you, then you collect all the possible order pairs. This is all the possible one, okay? Now, any subset of this order pairs is going to be called a relation. So a relation is a collection of order pairs. It depends how we're going to define it. Okay, so when you put these together, you say, oh, 2 is related to 4. 2 is related to 5, 3 to the load, etc. So a relation is going to be just a collection of order pairs. Any collection of order pairs is going to be called a relation. Everything we talk about, Starbucks, okay, Burger King, going to this Albertson, gas station, they are all definitions, are examples of relations. Relations because we have two quantities. This is the way we do it in mathematics. You have two quantities. The first one is free. You can derive as much as you like. But the second one, you have to pay for it. How are we going to pay for it? When you go to the gas station, the machine will tell you. But that machine is going to be the relation. We define the relation first, and then, of course, we get to the function. The function is the one you were talking about. I'll talk about it next time. Let's give an idea of order. I think that's one we have time today. Okay, any question? And so we'll review this for yourself. We give you definition of a relation and a function. For the function, we try to give it whatever we need. This is the one that previously we have chapter 7, we talk about it. But we try to make most of it over here. In chapter 7, then we have a couple of examples of functions and the relation that we use, in particular in computer science. We talk about those numbers. But we have more to talk about it. And that's it for today. Any question? And so get to know these. Okay, these are not difficult, as I told you. Get to understand it. The way you write it down are very crucial, because you know that it's the way you are going to write to communicate with your machine in future. Okay, that's it. See you on the next class on Wednesday. That's one. Okay, any question? Check the syllabus. If you have any question, let me know. Otherwise, see you on, nice meeting you all. See you on Wednesday. Have a good one. Bye-bye.
All right,
Thank you,
see you,
Professor.
Randy. Thanks.
Thank you.
Thank you, Professor.
Thank you. Bye-bye.
Thank you.
Thank you.